So now we study the very important concept of vector multiplication. How do you multiply vectors? Now there are three ways in which vectors can be multiplied, but none of them follow the usual algebraic multiplication rules. The first method where you can multiply vectors is when a vector is just multiplied by a scalar. Say there is some vector A and it is multiplied by some scalar number S. So you get a vector A into S, where each component of the vector A gets multiplied S times. Now the direction of the vector AS will be in the same direction as A if S is positive, and it will be in the opposite direction if S is negative. So this is all about multiplying a vector by a scalar. Next we come to when a vector is multiplied by another vector, and there are two such cases. One case is when two vectors multiplied to give us a scalar, and another case is when two vectors multiplied give us a vector. Now when two vectors are multiplied to give us a scalar, it is called scalar product. It is also called dot product. And we write it like this: A dot B. A is a vector, B is a vector, A dot B denotes scalar product. And what is it equal to? It is defined as, A dot B is defined as magnitude of A into magnitude of B into cosine of the angle between the two vectors A and B. This is scalar product. Now the best example of scalar products in physics is example of work. Work is the dot product or scalar product of force and displacement. So work is force dot displacement, and so work is F into S into cos theta, and where theta is the angle between the force and the displacement, and if theta is 0, then you get work is force into displacement. Similarly, another example is of power. Power is force dot velocity. That's what is power. Now scalar product has certain properties. One property is scalar product is commutative. That is, A dot B equals B dot A. Why? Because A dot B is AB into cos theta, and B dot A is BA into cos of the angle, which will be 2 pi minus theta or 360 minus theta. And this 360 minus theta becomes cosine of minus theta, which is the same as cos theta. So we have A dot B is equal to B dot A. So this is another law of vector algebra that scalars obey. Scalar product is commutative. And we also see that A dot B plus C equals A dot B plus A dot C, which we can prove. This is a law which is called distributive law. So we say scalar product also obeys the distributive law. Now if two vectors are perpendicular to each other, the angle between them is 90 degrees, then A dot B is AB cos 90. Cos 90 being 0, it becomes 0. So if the dot product of two vectors A and B is 0, where each of A and B are non-zero vectors, then we can say that the two vectors are perpendicular to each other. Now what if the vectors are parallel to each other? Then the angle between them is 0, then A dot B becomes A into B. So dot product of a vector with itself, A dot A, becomes A square, square of the magnitude of the vector. So now let's come to the unit vectors. What about I dot I, J dot J, K dot K? It should be square of the magnitude. Each one has magnitude 1, so square of 1 becomes 1. And what about I dot J, J dot K, K dot I, or J dot I, K dot J, I dot K? they will be equal to 0 because each one of them are mutually perpendicular to each other. So now suppose I wish to find A dot B in terms of the components of A and B. Let A be this three-dimensional vector having components ax, ay, az, and let B be a three-dimensional vector having components bx, by, and bz. Then A dot B, if I write out A dot B, A dot B, and then we multiply out each term. Each term is multiplied out. And the dot product is taken. Remember, these ax, bx are scalar numbers. These are the vectors. So you have the dot product with the vectors. I dot I is 1, I dot j is 0, I dot k is 0. So out of all these terms, the ones which remain are ax, bx, ay, by, and az, bz. So we get A dot B equals ax, bx plus ay, by plus az, bz. So from here, we can even calculate the angle between the two vectors A and B. The angle cos theta, the angle between the two vectors A and B, is A dot B upon magnitude of A into magnitude of B from the definition. Now again, A dot B we just now saw is equal to this divided by magnitude of A, magnitude of B. So that's all about scalar product. Now we come to vector product, where two vectors multiplied give us a vector. Now how do we define vector product? It's also called cross product. It is written as A cross B. So when you write the multiplication sign for vectors, like for numbers, when we multiply, we just randomly write either a dot or a cross. In vectors, a dot means something, a cross means something different. So we have to be very careful about which symbol we are using for vector multiplication. So what is A cross B? A cross B produces a vector C, whose magnitude is magnitude of A into magnitude of B into sine of the angle between the two vectors, where the angle, this angle between the two vectors, is the smaller of the two angles. So if I have a vector A which goes like this and a vector B which goes like this, then this is also an angle between A and B, and this is also an angle between A and B. So when we say the smaller of the angle, we actually mean this angle phi between the two vectors A and B, the smaller of the two angles. Now what about this? This was about the magnitude. What about the direction? The direction of C is perpendicular to the plane containing the vectors A and B. So let's find out how we can get the direction. Now these diagrams explain to us very clearly the direction of the vector A cross B. We use the right hand, and the fingers of the right hand first align with the direction of vector A and then turn towards the vector B through the smaller of the two angles, and the extended thumb gives the direction of the vector C. Now obviously the extended thumb points upwards, as we can see from here. A and B are in the horizontal direction, extended thumb is pointing upwards in the vertical direction. So this is the direction of the vector C, pointing upwards, outwards, towards us. So if I now have to find the direction of the vector B cross A, then what do? The fingers of the right hand again first align in the direction of the vector B, the right hand. Then curl into the vector A, move towards the vector A, through the smaller of the two angles. And the extended thumb gives the direction of the vector B cross A. So here we find the direction of A cross B is pointing upwards, vertically upwards. The direction of the vector B cross A points vertically downwards. Magnitude of A cross B is magnitude of A into B into sine of this angle. Magnitude of B cross A is magnitude of B into A into sine of the same angle. So the magnitudes are the same, but the direction of A cross B is exactly opposite to the direction of B cross A. Hence, we say that the vector A cross B, or rather the vector B cross A, is minus the vector A cross B. This is a very, very important rule, that vector cross product does not obey the commutative law. A very important rule. So now what happens when we consider the unit vectors? Let's see what happens when we consider cross product of the unit vectors. So I have the unit vector I pointing in this direction towards the right in this plane, J pointing in this direction also in the same plane, and K pointing upwards, perpendicular. So this is x-axis, this is y-axis, and here is the z-axis pointing vertically upwards is the z-axis. So now if I do I cross J with the right hand, I cross J, and I have the vector I cross J pointing vertically upwards towards the direction of K. Magnitude of I cross J is 1, and the angle sine 90 is also 1. So I have I cross J is 1 into 1 into 1 pointing in the direction of K hat. So we say I cross J is K hat. Now what about J cross K? This is J, this is the direction of K, and I have the extended thumb pointing in the direction of the vector I hat. So J cross K is I hat. And what about K cross I? This is the vector K cross I. K upwards cross I with the right hand, and the extended thumb points in the direction of the vector J. So K cross I is J. Now I cross J is K, so J cross I will be minus K. J cross K is I, so K cross J is minus I. And K cross I is J, so I cross K will be minus J. Now this dot is a symbol which signifies that the vector points vertically upwards towards me. And if it's in the opposite direction, then it is denoted by a cross. Cross signifies a vector pointing away from me, perpendicular to the plane. This is direction of minus K hat, shown by a cross. So now if I have to denote some more properties, what's an example in physics of vector cross product? Torque, R cross F, vector cross product, which we will learn later on. Angular momentum, R cross P, which we will also learn later on. What are the properties of vector product? One property we just now saw, that it does not obey the commutative law. A cross B is not equal to B cross A. A cross B equals minus B cross A. But it obeys the distributive law, vector cross product. That is, A cross, this should have been B, B plus C equals A cross B plus A cross C. Now, what if the vectors are perpendicular to each other? Then A cross B is equal to A, in magnitude of A cross B is A into B. What if the two vectors are parallel to each other? Then A cross B will be 0. So cross product of two parallel vectors will always be 0. What about cross product of a vector with itself, A cross A? Again it is 0, because the angle between the two is 0. And here are the relations between the unit vectors, which I just now described. Now suppose I have two vectors in in 3 dimensions. Let's find out what is A cross B. This is vector A cross vector B. And we multiply out each term. Each term is multiplied out. Each term is multiplied out. Now out of these terms, I cross I will be 0. Again, j cross j will be 0. And k cross k will be 0. I cross j is k. I cross k is minus j, and so on and so forth. So finally, when we substitute all of this, this is what we get in terms of the components. So we group the I component, the j component, and the k component. And this can be written in a mathematical form, which is called a determinant, where this is the first row, this is the second row, this is the third row. First row has the unit vectors, second row has the components of the first vector, third row has components of the second vector. And the meaning of this is I into AYBZ minus this plus j into this plus k into this. That's how we write out the vector cross product.